Hello everyone. In this video, we are going to look at column buckling. So if you have seen beams that we talked about them in the past, on the beams, the load that we apply is a lateral load, is perpendicular to the axis of the beam, and that will cause this deflection, okay, or this lateral displacement. Now, in buckling, it's different. The load that you apply is axial. It's not lateral load, it's axial load. And it should always be a compression force. If it's tension, nothing gonna happen. But if you apply compression on basically a beam or a column in general, then they can start, after this load passes some level which called critical limit, you see they start bending laterally and this deflection keeps going. So unlike the regular deflection where under a specific load, the deflection is a fixed amount, correct? So here, if this P is a fixed P, then this deflection is a fixed amount, right? The curve is fixed, static. But in buckling, once this P passes some critical limit, this deflection starts getting bigger and bigger, and the system goes unstable until the system will collapse. Okay, so the deflections due to buckling is gonna be non-static, and it's gonna keep increasing in an unstable manner until the system collapses. So you have seen examples of that in real life. Now these are the specimen in lab, but in real life probably many of you put some pressure on your soda can that is empty, and you could basically bend it like this. Or if you have a straw or something, right, and you put so much pressure on the straw, you see that you could bend it and break it. Or on anything else, as long as most of the time they are tall and they are slender, so their cross section is not big. Those two factors, large length and small cross section, will cause the load, this critical load, to be small, as we'll see in the Euler's formula, and the system to buckle, basically. So let's look at this. First, we want to talk about this stability issue that I just mentioned. So here is the beam that we want to study. So there is a pin here and there is a roller there, and this P here is the compression load that is going to make the system buckle. Now, instead of studying this first, just to show the notion of stability, we assume that this column is made of two pieces, piece AB and piece BC, and these two are connected with the pin, and at the pin we have this torsional spring with constant beta R. So of course, when the beam is gonna break in half and it's gonna deflect like this, then this torsional spring is gonna put some moment in the system, and it wants to put it back to the upright position. Okay, so you show this internal resistance by a torsional spring just to simulate the behavior of it. Good. Now, here, if I get very small changes in the angle, so instead of being perfectly upright, if I get these two pieces of the beam to have some small deviation from vertical angle, and that deviation is called theta, just 1 or 2 degrees, a few degrees, what's going to happen? Well, in this case, clearly, the moment that this torsional spring is going to apply is going to be its constant times the total change in the angle of it. Initially, the angle it has was 180 degrees between these two pieces. Now the angle is 180 minus 2 theta, because there is 1 theta here, there is 1 theta here. So the total change in the angle for this, or the total torsion angle, is 2 theta. So if you multiply 2 theta by beta, that is the total resisting moment that this torsional spring is applying and trying to bring it back to the upright position. Good? This is what you get from the spring. On the other hand, if you go ahead and cut here at the location of this beam, this member, and look at the free body diagram of one piece, let's say the top piece here, well, the forces that you have, okay, are this P force, the external P force that is going to buckle, and there is, of course, a shear force here and a bending moment at that location. Now, clearly, not shear force, axial force in this case. This is the shear force. So shear force is 0, but the axial force has to be equal to P upright to cancel that. And then this moment here, the bending moment, can be found by P times this distance from point B to the P, this distance, which is clearly, if each one of them is L over 2, it is going to be L over 2 sine theta. And since theta is small, we can just say L over 2 theta. Okay, so this is that distance here, L over 2 times theta. Again, assume that theta is very small, times P, that is your bending moment here. Good. Now, this bending moment is, by setting that equal to the bending moment of the torsional spring, the one that is bringing the system back, so I'm going to plug it right here, you can see that the P that you'll find is going to be basically 4 beta R over L. So this is the P or P critical. Now, what happens in this system? In this system, if the P that you're applying from outside is bigger than this P critical, what's going to happen? Well, on one side, if you look, on one side, this P is going to cause, if you look at it, that P about point B is going to cause a counterclockwise moment, right? And counterclockwise moment means this member is going to bend further and further down. So the deflection is going to increase because these members are going to bend further, right? So P times that L over 2 theta is the one that is, or L over 2 sine theta for bigger angles. This is the one that is causing the members to bend further laterally. On the other hand, MB, which is 2 beta R theta, this is the one that is resisting from that torsional spring and want to bring the system back. So the stability of the system is a balance between these two moments, this one and this one. And this one is, of course, 2 beta R theta. So depending on which one is bigger, one of them will dominate. Now, when P is bigger than this P critical, clearly this term is going to be bigger than MB. So the total moment about B is going to be counterclockwise, and counterclockwise means this deviation is going to continue to increase and the system goes unstable. So the system starts laterally deflecting more and more until it collapses. So that is what I just discussed here, that if P is bigger than P critical, the system is unstable. Now, one thing we have to pay attention to is, regardless of how much P is, if the system is initially perfectly upright, so these two have 180-degree angle between them, clearly some of the moment about point B is going to be 0. Because this P is passing through B and these two members have not changed angle, so this is 0. So the system is at equilibrium, and these angles theta will not come into existence if we can keep the system perfectly upright like that. Okay? But as soon as there is small angle, a fraction of a degree, if there is a fraction of a degree angle between the line of these members and the line of P, that is enough with this much of P to cause the system to go unstable and for the deviation to continually increase. And you might say, well, can't we always make sure that the load P is along the column? Well, the matter of fact is no. Because if you look at many of the columns in real life, let's say, for instance, you have a C-beam or just like a simple pocket like this, a cross section. Okay. So this is a column under a building or anything. And this is the line that your P should be perfectly along. Now, if the load that I'm applying here is the equivalent of this distributed load on this cross section, if that is exactly the equivalent load is in the middle, yes, of course, it's fine. But most of the time, the load is not perfectly uniform, or the member is not made perfectly upright. There is just a small bending somewhere in the middle. All you need is a fraction of a mil bending in the manufacturing for this buckling to start. So because nothing is perfect in reality, you can never make sure that the line of P and the line of the member are exactly collinear. So there is always a chance of a small deviation, and once your P is bigger than P critical, that deviation will continuously increase. That's called instability. On the other hand, if P is less than P critical, this time this MB will dominate, and so the MB will always cancel the P, so the total moment is going to be clockwise, so the system will go back to the upright position. So we say the system is what? Or the column is stable. And of course, if P is equal to P critical, then you are on the verge of going stable or unstable, so we call it neutral equilibrium. And the system is basically marginally stable or marginally unstable. So what we really need to find in buckling cases is this critical load. We need to make sure this thing never happens. Your P always falls below P critical. So even if there is any small deviation, it never will grow. Okay? Now, the formula that we found here was based on this virtual or artificial torsional spring. In reality, there is no torsional spring. We have to find an equivalent for this formula, a realistic formula. So for that, here, the first type of column that we are going to look at is two ends are pinned. And this is what you can see here. A and B are both pinned, and B is allowed to go up and down, so the compression can happen. Now, there are some assumptions that we make here. One is the XY plane is the plane of symmetry of the column. So the column here is symmetric about the XY plane. Any bending will happen in the XY plane. The material operates in the elastic region. The lateral deflection initially is small, and the column is initially perfectly straight. Okay, so we make a bunch of assumptions. Many of them are not super realistic, like initially perfectly straight. Okay, but here, just to derive some formula, we go with that simple thing. And when I say lateral deflection is small, that means initially small, okay? Because once you go unstable, it is going to go up and gets bigger and bigger. So now, how do we find any formula for this? Well, to do that, here, we are going to use the formulas we learned for bending of the beams, lateral deflection. And this lateral deflection of the beam after the buckling starts, I'm going to call it V, just like the beams. The total length is L, the compressive force is P. So now what I do is, just like previous case, I'm going to cut the beam here at arbitrary distance X. And there are two forces that are needed here to keep it at equilibrium. One is the force P, one is the bending moment M, just like this scenario here, right? Remember, it's the exact same thing that we had for equilibrium. We need these two. So that's the exact same thing here. Now, what is M, what is P in this case? Well, this force P has to be equal to the external P, of course, to hold the equilibrium. But M clearly is equal to what? M equals P times this distance from here to here, and that is V. So P times V with the negative sign, that is equal to M. Because if you take sum of the moment about here, M and then plus PV equals 0, so M equals negative PV. That's your bending moment. Now, if you remember from bendings of the beam, if initially nu is small, I can show that EI nu double prime is equal to M. If you remember, this was the equation for deflection of the beams that we double integrated to get V, correct? If we had the bending moment. So now that bending moment is going to be plugged into here, and you get this second order linear differential equation. EI nu double prime plus P nu equals 0, or V you might call it. Clearly, you see this is second order linear differential equation with constant coefficients EI and P. And it's homogeneous, so there is only a homogeneous solution. To find the homogeneous solution, we need to form the characteristic equation. In this case, it is going to be basically EI S squared plus P equals 0. In this case, instead of S, we called it K, so it could be K squared. And the roots of that, okay, are clearly going to be K squared is going to be actually negative P over I, not positive. It's going to be negative P over I, right? Because you have to take it to the other side. And so a square of a number is negative. That means K is complex number, right? So K is going to be positive negative I times the square root of P over EI. And when the roots of the characteristic equation are complex number, you know the homogeneous solution is going to be a sine and a cosine. C1 sine of kx plus C2 cosine of kx, where k is this I times that square root. C1 and C2 are two unknown constants to be found from the boundary conditions. Now, of course, at x of 0 and x of L, the lateral deflection nu is 0. So we plug them here. If nu of 0 is 0, that means C2 should be 0, clearly, right? And once C2 is 0 at L, you plug in here, it's going to be C1 sine of KL equals 0. Now C1 cannot be equal to 0. If C1, because you see here, this is the product of two terms. If it's 0, the first one is 0 or the second one. The first one cannot be 0, because if that's the case, then nu is going to be all 0. That's the trivial solution. So C1 cannot be 0, so sine of KL should be 0, which is what you can see. And that means KL is an integer multiple of pi. From here, I can find K. K is clearly n pi over L. Okay, so that K, that root, I found it. Now, pay attention that K squared is negative P E I, correct? And of course, so from here, if we just look at the magnitude, P over EI equals, now remember that K squared is going to be basically P over EI times a negative 1. And here, okay, this thing is in magnitude, this is K squared, and this is equal to, because K is n pi L, so it is going to be n pi over L squared. And if you multiply both sides by EI, you can get P to be n squared pi squared over L squared times EI, like this formula, where n can be any integer number. Now, of course, if we want the smallest load that is valid in this solution, we should go for n of 1. So if you plug in n of 1, that's where you get your load, P critical, to be pi squared EI over L squared. This critical load is called the Euler load, and this formula is called the Euler's formula. And of course, if you plug in that K back into your shape of the buckling, you see that the solution for the shape of buckling is going to be sine of Kx. And K is n pi over L, and n is 1. So this shape of the curve of the buckling in general is going to be a sine function. So the way that this guy is going to curve, this one, this curve function is a sine function. Sine of what? Sine of pi x over L. Is that correct? Well, plug in x of 0 in it, it's sine of 0, 0. Plug L in it, it's sine of pi, it's also 0. So you see both boundary conditions will fit into this function here. Okay, so the shape of the buckling is a sine function, and the critical load is pi squared EI over L squared. Good. Now let's go back to the thing I mentioned in the beginning of the video. I said the longer the column is, the smaller the load you need to bend it laterally to buckling. You can see that here. Look, L is in the denominator. So L bigger means P critical smaller, and not in a linear manner, in a quadratic manner. So you make a column 2 times taller, the load goes 4 times down. Okay, so clearly L is inversely affecting in a quadratic manner the critical load. On the other hand, you see the material. The stronger the material, of course, the stronger the critical load. And then I depends on the thickness of the beam and the height of the beam. So the bigger the I, the bigger the cross section, the bigger the critical load. And the more slender it is, which means I is small, in a linear manner, P is gonna go down. So if the column is very slender and very tall, this load is gonna be very, very small. You can easily bend it, okay, and buckle it. Okay, now that we saw the important formula, pi squared EI over L squared, one other thing we have to pay attention to is the stress due to this critical load. Well, if P is equal to critical load, if you divide that P by the cross section, that is going to be the critical stress on the column when the buckling starts, and all you need is to divide that formula by A, which is this guy here. Now here we do some recall from our previous lectures, especially in statics. If you remember, if I divide I, the second moment of any cross-section, by the cross-section and take a square root, that was the definition of radius of gyration. So here, this I over A, I can write it as R squared. So it is going to be pi squared E R squared over L squared. I can write it like this, where R is the radius of gyration. And then I can bring R squared to the denominator, and I can write it like this. Okay, which is what you can see here. Now this L over R is called the slenderness ratio. It's an important parameter, which has both of those important factors I just talked about, the length and the moment. The bigger the radius of gyration, what does it mean? It means the bigger the critical load or the critical stress. The bigger the length, the smaller the critical stress. So you see, sigma critical is inversely proportional to the slenderness ratio to the power 2. So if you plot sigma critical versus a slenderness ratio, you're going to get this curve here. This 1 over x squared curve, which is called the Euler curve. Now this curve here is plotted for structural steel, for which the Young modulus is, as you can see, 30 times 10 to the 3 ksi, or 30 mega psi. Okay? Yes? And the other thing that you have to pay attention to is the maximum allowable compressive load for structural steel is 36 ksi. So what does that mean? Means when I'm putting a compressive load on a column, which mode of failure do I expect it to show? Would it go through buckling, or would it simply fail under maximum sigma? If this maximum sigma reaches sigma allowed in compression, guess what? It is gonna start failing under compression before it even reaches a critical level. So what I need to do if I want to know whether it fails under compression or it fails due to buckling, I need to mix this Euler curve with this constant value. Okay? Yep. So if my slenderness ratio, it only has meaning until I reach the level of failure under compression. After that, or behind this number, behind this slenderness ratio for the intersection of these two values, here there will be no buckling. This will be failure under compression. This region here on the right, this is the buckling region. So Euler curve only goes to the intersection of the maximum allowable compression load of that material and wherever this quadratic curve is intersecting it. Okay, this is only this region that is buckling. The region on the left is failure under compression. So this is very important. When you're looking at columns, you have to make sure none of these failures is happening. Okay. Now, the next thing I need to talk about before we look at one example is, here we said I. If you look at this formula, we said I. Which I? That's one important thing that we have to consider. When we said I here, what I? If you look at any cross section, it has two eyes. So here, if this is the cross section of the column, there is one for 1, 1. There is one for 2, 2. Which one of them should be placed in this formula? The answer is always the smaller one. So if this is the smaller one in this case, or it's the bigger one, you always put the small. Now in this case, actually 1, 1 is bigger because the section is taller along the 2, 2 direction. And if you remember, if this guy is H and B, this I1, 1 is what? This is BH cubed over 12. This one is HB cubed over 12. And if we assume that H is bigger than B, clearly because this one has H to the power 3, then I1 is bigger in this case. So the I that should go in that formula in this case is the smallest one. So this I, when we say I, this is I of minimum, the minimum on that cross section, not the maximum one. So in this case, the bending is going to happen about the 2, 2 axis. So if I have to draw this for you, this is the cross section. If I apply my load P, which direction is that going to bend? Is that going to bend this way to the side, or is that like this? Okay. Something like that. Or is that going to bend in this direction like this? Right? Which one? So is that going to go this way or is that going to go this way? The answer is this one, because this has the smaller I about its axis. Okay, so the way it is bending, the direction it is bending is about the I of the minimum axis. Now here, let's look at one example. So here we have a slender bar ABC, which is supported here basically at the end. It's a double pivot, and actually again this roller is just to allow the motion, and the whole length is 8 meters. But what we did, in order to change the length that is exposed to lateral bending, we put some support here in the middle and literally converted it into 2 smaller sections, each one of length 4. That means I can increase my load by a factor of 4 times, correct? Because when length is going down by a factor of 2, the critical load goes up by factor 4. So one way that you can support your columns is by reducing the free length over which the load is applied, and the best way to do it is to provide lateral support along the column. That's the best way to reduce the effective length of the column. And this is what you're doing here. Now, the column is made of steel with 200 gigapascal Young modulus. The cross section of it is W 200 by 34. The proportional limit for compression is 300 megapascal. And as I said, L is 8 meters. We want to know how much is the maximum load you can apply if you want a safety factor of 2.5 for buckling. Okay, so here we need to get some information. The first thing is you are going to look at the basically I-beams and look at different cross sections. And if you look at different cross sections, there are tables at the end of your solid mechanics book where you can see different beams. The tables for different beams are there. You can see their centroid, you can see their cross section, you can see dimensions, and you can see the moments. The one that we care about are the moments. So what we need to get are I11 and I12 from this cross section, from the tables at the end of your solid mechanics book. And if you look, this is 2690 centimeter to the 4, and the other one is just 178. And also, if you need the cross section, also cross section for this guy is 43.6 centimeters squared. You see, so these come from the W200 by 34. So they are tables like this, okay? And if you can see, you can just follow the W times what, and then you can see there is mass, there is area, depth, width, thickness, everything, and then there are I's for the basically the XX and the YY. So all of the information are available in those tables. So I got all of these. I also have E. And now the question is, how much is the critical load in this case? So the P critical, remember, it is pi squared EI over L squared. Now in this case, since you brought it down into two smaller parts by adding the support, the actual L you have to use is L over 2. As I said, that makes your critical load 4 times bigger. The question is which I will go there. As I said, always the smaller one is determining everything. So this is going to be I22. Okay? And do I have all the numbers now? Yes, I have E, I have I22, I have L. So from here, I should be able to calculate my P-critical to be 220 kilonewton. This is the load. If I go above it, the buckling will start about basically axis to 2. Good? Now, what is the sigma critical? The sigma, due to this P critical, you have to just divide it by the cross section. And if you do that, this number is going to be 190.4 megapascal. Yes? Okay. So, now compare this against your proportional limit, which is 300. This is less than 300. What does it mean? Means the system is not going to fail under compression. The system is going to fail under buckling. So you are clearly in the right side region, okay? You're clearly below that threshold of 300. So you are literally in this region somewhere there, okay? You're here on the right side. Now it says how much is the total force that you can have. if you want a safety factor of 2.5. What does 2.5 means? Means my force should not be as big as the P critical. It should not be this much. Because if I'm at that, the safety factor is 1. Basically, anytime I pass that number, the buckling starts. My actual allowable force should be the P critical divided by the safety factor, which is 2.5. So I have to divide that 220 by 2.5, and that means it's 88 kilonewton. So if my load on the column is 88 kilonewton, not only, of course, I'm not gonna basically yield under compression, also I'm not gonna buckle with a safety factor of 2.5. So this is the maximum force you can apply on this column. Now remember, if this if this middle support was not there, then you're gonna get 4 times bigger than this. So this guy is gonna go to 880, and that means this guy is gonna go to 61.6, correct? And that is way bigger than 300. Even if I divide that by a safety factor of 2.5, my load is going to be 304 point something, and this is bigger than 300. Okay, and that means it is going to first basically surrender to compression, not to the buckling. So that's why we are supporting it here, to limit the failure to buckling, and by using a big safety factor, we make sure the buckling will never happen. So supporting the columns in the midway is an effective way to reduce the length that we use in the Euler formula. Now, the last thing we want to discuss is, what if the boundary conditions of the column are different than pivot-pivot? Because this is what we just studied, pivot-pivot, and we found the formula is pi squared EI over L squared. What if one end of it is cantilevered and the other end is free? So it's fixed free column. What about that? Well, if you do calculations for this one, you'll find that the denominator is going to be 4 times bigger, which means the critical load is going to be 4 times smaller. Okay, so this one is going to buckle much easier than this one does, because this end is free. If you do it with both fixed, then it's going to be 4 times bigger actually. So you're going to get to tolerate a lot more before buckling. And if you do it with one end pivot and one end fix, then this is going to be 2 times bigger than this scenario, 2.04. So what we can do is we can combine all of these 4 scenarios into a simple formula of P squared EI over L effective squared, where L effective is a constant K times L, and that K depends on the boundary condition. So in this case, I can say K is 1. In this case, I can say K is 2 because L effective is 2L. In this case, I can say K is 1/2, and in this case, that's basically the 1 over the square root of that. And so these are the Ks, or the L effectives. So if you have different boundary conditions, then we can find different effective length, and we can still use the great Euler's formula. So hopefully this introduction to column buckling was useful to you. You learned where the Euler formula come from, what is the slenderness ratio, what is the Euler curve, what do we do for different boundary conditions, about which axis the system is going to buckle, and a few other useful things. Thank you so much for your attention. I'll see you in the next video.